This particular figure is attempting to give you additional information about the rules of probability that you read in the book, and sometimes that's referred to as the and or rule. Now we're going to focus on the and rule, and if you're asking what's the probability of a particular outcome, and you use the word and to link two different events, then the mathematical implication is you multiply probabilities. So for example, if I ask when flipping a coin, what's the probability of getting a heads on the first and getting a heads on the second flip? Then the probability of getting a heads on the first flip is 1/2 times the probability of getting a heads on the second flip, which is 1/2. So the cumulative probability of both of those events happening is 1/2 times 1/2, which is equal to 1/4. So when we use the word and in describing the relationship between two events, then we're indicating multiplication. Now very briefly, the or rule means there are different ways of the same event happen, or different ways of events happening, and instead of multiplying their probabilities, you add them together. So for example, if we go back to the idea of flipping a coin, if I said, what's the probability of getting heads or tails? Well, the probability of getting heads is 1/2. Since I have an or, we add the next event. The probability of getting tails is 1/2. So the probability of getting heads or tails is 1/2 plus 1/2, which is equal to 1. And that should make sense because when you flip a coin, you're either going to get heads or you're going to get tails, and that's the situation 100% of the time, unless you've got a coin that's kind of funny. So, but that's a little summary of the rules of probability. And again, we're going to be focusing on the and rule, which implies we multiply. So this particular figure is showing you information about a dihybrid cross, which means we're crossing two particular traits. In this case, we're dealing with the fur color, which is black or white, as we'll see in the offspring in the step 2, or it's dealing with fur texture, which is smooth or curly. So the thing to remember in this dihybrid is the assumption is each of the traits is segregating independently. In other words, there is no genetic linkage, and that's going to be the case that we're going to consider. Linkage is a more advanced topic that if you take another genetics class, you'll get into in more detail. So because of independent assortment, what we can do is take the parental genotypes, and instead of dealing with them as a combination, and I will show you in the next figure how you could do that, we go ahead and break them into the two traits. In other words, my first parent is heterozygous for color. My second parent is heterozygous for color. So we've already said if I cross two heterozygotes, I'll get a 3-to-1 ratio. And so that's what's being shown here. I would have 3/4 of the individuals being black. They would have at least one dominant allele. Now, 2 of the 3 would be heterozygous, 1 of the 3 would be homozygous dominant. But at this point it doesn't matter because all we're focusing on is phenotype. So 3/4 would be black, 1/4 would be homozygous recessive white. It would be the same situation if I looked at simply fur texture. I would end up with 3/4 with the dominant phenotype, which is smooth, 1/4 with the recessive phenotype was curly. Now, if I asked you what's the probability of getting a black and smooth offspring, then what you do is you take the probability of each event. The probability of getting black is 3/4. The probability of getting smooth is 3/4. So the cumulative probability is 3/4 times 3/4, which is equal to 9/16. So 9/16 of your progeny will have at least one dominant B and one dominant S. If I asked you what was the probability of getting a black and curly offspring, then it's 3/4 for black, 1/4 for curly, so 3/4 times 1/4 is equal to 3/16. So we would expect 3/16 of the offspring to have at least one dominant B as well as both recessive S's. Now, if you look at these probabilities, you'll notice 9/16 are dominant-dominant, 3/16 are dominant for one trait and recessive for the other. So in other words, I have dominant for black, recessive for curly. I have recessive for white and dominant for smooth. And then 1/16 will be double recessive. In other words, white and curly in this particular example. So those are classical Mendelian ratios for a dihybrid cross in which I have two different genes, each with two alleles, and complete dominance being shown at each allele or each gene. In other words, all I need is one dominant allele and I show the particular phenotype. So for those of you that had biology before, you may have heard of that referred to as a 9 to 3 to 3 to 1 F2 ratio. So again, rather than doing a big Punnett square and writing out 16 options, you can use rules of probability to make the process much easier. Now, in the next figure, I'm going to actually show you the complex Punnett square, and hopefully after viewing that, you'll have a sense of how much easier this particular process works. But again, the only reason it works is because we're assuming independent assortment of the two traits. In other words, what happens at the color locus has no influence on what happens at the texture locus.